of the problem solving, and you will have another one during the week to go over the, thank you, to go over the stuff that we do like during this week that's also going to come up in the exam. The first thing is what's on this exam, and this is not a comprehensive list. We do not see the exam before you guys do, but this is kind of what usually comes up in the Unit 2 exam. So you will definitely see phase transitions and phase equilibrium, those graphs where you see what happens to the phase as you change the temperature. You will see the connection between phase equilibrium and intermolecular forces. So you will kind of need to use intermolecular forces to explain what's happening on a molecular level. You will see reaction equilibrium in the gas phase. You will see entropy and the second law of thermodynamics. And you will also see free energy, free Gibbs energy, and the thermodynamic equilibrium. So the first thing we will talk about is the dynamic equilibrium. The dynamic equilibrium is basically when we write the reaction as like products going to reactants, and we have these two-way arrows, which basically means both the forward and the reverse reactions are happening at the same time. And at the point where you're at equilibrium, the rates are equal to each other. So when is the equilibrium? Your forward rate is equal to the reverse rate, or you can write it in another way where you say the forward rate constant times the concentrations of the products is equal to the reverse rate constant times the concentrations of the reactants. And this is basically giving you the competition between forward and reverse reactions. So your initial concentrations have no effect on the equilibrium conditions. So you can start with either like all products, or you can start with all reactants, or you can start with like a mixture. And as long as you're at the same temperature, your reaction will have the same end concentrations, right? So you will get to the same equilibrium. Your K equilibrium value is going to be the same as long as you have the same concentration. What it affects is the time it takes the reaction to reach the equilibrium, because obviously if you start from a very far away place where you only have reactants, for example, it's going to take a while for the reaction to get to the place where you have the product versus reactant ratio that is required for the equilibrium. If you start from somewhere close, then it's going to take less time. And these graphs are kind of like generally showing you what happens to the concentration and the rates when you reach the equilibrium. So on the left side, you can see what happens to the concentrations. When you reach an equilibrium, obviously you won't necessarily see a change in the net amount of reactants or products. So your graph will either like increase or decrease in the beginning when you're not at equilibrium, and at the point where you're at equilibrium, your graphs will flatten out. And you can see it in both of these. And if you look at the graphs on the right, these are kind of showing you what's going to happen to the rates. So the relative rates may be different when you're not at equilibrium, but at the time when you reach the equilibrium, and I'm not sure if you can see my mouse, but there's a point at the graph where the two rates are merging to each other, which means they're the exact same. And at the point where they start merging is the point where we get to equilibrium. And at the equilibrium, the rates have to be equal to each other. Now we can talk about what the equilibrium constant is. Basically, the equilibrium constant is gonna be a mathematical expression of like the product versus reactant concentration ratio at equilibrium. And law of mass action, which I don't know if we mentioned this in class, but this basically tells you how to write the equilibrium. So we did do this. We may not have named it the same way, but as you can see, there's a reaction, and this equal sign is supposed to be a plus. So A plus B going to C plus D. And when you have a reaction like this, you can write the K equilibrium in 3 different ways. The first way is basically saying forward reaction constant divided by the reverse reaction constant. The second way is writing the concentration of products raised to the power of their stoichiometric coefficients divided by the concentration of the reactants raised to the power of their stoichiometric coefficients. And then you can also do the same thing with pressures. But the important thing with pressures is that Kc is never going to be equal to Kp, but you can relate these two to each other. And you can basically just use PV is equal to nRT. And we know that concentration is moles divided by volume, right? So you can move the V to the other side of the equation, and you will basically get concentrations times RT for each pressure. So you can put that pressure value for each concentration, or you can do it more generally. If you're already given Kc or Kp, you can do it with this like expression we've written on the bottom. I don't know if you can see it. Okay, Kp is equal to Kc times RT raised to n. And delta n is going to be the coefficients of products minus the coefficients of reactants. And this can be a negative number. Don't let it confuse you because it's just coefficients. Did we miss anything in this slide? So K equilibrium is not affected by the initial conditions. We kind of already mentioned that. And all reactions are technically reversible. So even if the reaction goes to completion, it basically just means that it has a very high K equilibrium value. But it is still reversible. Like if you can somehow get to a condition, a situation where you can make the reverse reaction go a little bit, like accelerate a little bit faster, you can obviously get the reverse reaction too. This is again about our equilibrium constant. When you write your balanced equation differently, your K equilibrium value can change. And we kind of saw that in like one of the power set questions or PhD questions, I'm not sure. But what you're basically doing is that if you have a given set of stoichiometric expression, and if you, let's say, like multiply every number by 2, what you're doing is that you're manipulating that equation mathematically. So your K equilibrium value is going to be a different number, but it's basically going to be the same K equilibrium value you would initially get raised to the second power. And that does not change anything about the equilibrium itself, because that is a mathematical expression we're using on a paper, and that has nothing to do with the molecules are doing. The molecules do not know how you're expressing this. So it's not going to change the equilibrium. It's only going to change the numerical value you get for K equilibrium. And another important thing is that equilibrium constant expression only depends on gases and aqueous solutions. So if you have a solid or a liquid, you would just put 1 for their concentrations, which basically means they're not affecting this value at all. And we have our 3 ways of defining an equilibrium. So you can say K equilibrium is equal to the concentration of products divided by the concentration of reactants. You can say it's the forward reaction constant divided by the reverse reaction constant, or you can say at equilibrium, your forward rate is equal to your reverse rate. And there are different ways of like interpreting these. So let's say you're given a K equilibrium constant that is larger than 1. What is that going to mean? You can look at our first equation and say, well, for this number to be larger than 1, I should have more products than reactants. And you can look at the second expression and say, for this number to be larger than 1, I should have a bigger Kf than Kr. And you can do the same thing for when K equilibrium is smaller than 1 or when it's equal to 1. So these are kind of like useful expressions to kind of talk about these numbers. There are different factors that's going to affect K equilibrium. Obviously, like I just mentioned, the numerical value is dependent on the balanced equation and how you balanced it. And the numerical value may change if you decide to balance it in another way. But also there are things that affect K equilibrium and the equilibrium itself. And one of those things is a change in temperature. So what you need to know is that if you have an endothermic reaction, increasing the temperature will increase the K equilibrium. If you have an exothermic reaction, increasing in temperature will decrease the K equilibrium. And this can get a little bit tricky. So to understand this, we had these graphs in lectures, and I think these are the most useful ones. So you can try to understand why one rate is going to be more affected by a change in temperature than the other. So you can look at this graph, and this graph, the one on the right, is showing you a reaction where the reactants are lower in energy than the products. So you have your endothermic reaction. And what's happening is that when you have an endothermic reaction, you can see the distribution of the number of molecules on this other graph that's on the left. So the y-axis is the number of molecules with a certain amount of energy, and the x-axis is the kinetic energy. When you look at this graph, the red is the initial condition. In the beginning, you have like a lot of molecules with very low energy. And that low energy is not high enough to be the activation energy, which is going to be this blue line. The blue line is showing you the activation energy. So you have only a small amount of molecules that have enough energy to react. When you raise the temperature, you're shifting this whole graph, as you can see with this blue curve, and you end up with having a lot of molecules that have enough energy. So what's going to happen when you have an exothermic reaction is that you will start with something that already looks like this blue graph. So as you can see with the blue one, you already have a lot of molecules that have enough energy. If you move this graph a little bit to the right, if you shift it a little bit, you are still increasing the number of molecules. It's just that the increase is not as significant as you would have otherwise. So this is one way of thinking about this. And this is kind of like going off of that. The Kp increases with T for endothermic reactions and decreases for exothermic reactions. I think they meant K equilibrium. So when there's a decrease in temperature, and these two sentences are coming from Le Chatelier's expression, and we will talk about it a little bit more. When you decrease the temperature, you will shift in the exothermic direction. So another way of thinking about this is you can think of the change in temperature as a stress in the system. And if you decrease the temperature, what's the reaction going to do? It wants to increase the temperature a little bit back again because you introduce the stress and you want to get rid of that stress. So what can you do? If you shift in the exothermic reaction, your exothermic reaction will give heat into the system. So going in the exothermic direction is going to help you balance that decrease in temperature. And the same thing happens when you increase the temperature. You again introduce the stress. You have too much heat in the system. So what is your reaction going to do? Your reaction will shift in the endothermic direction so that you can use up some of the excess heat that was introduced. And K is related to temperature by the Arrhenius equation. It is an important equation, and this is one way of writing it. There are a couple different ways. And the rest is a little bit more related to the previous graph, but I'll just repeat them. So activation energy is different for forward and reverse directions based on whether they're endothermic or exothermic. Activation energy is larger for endothermic versus exothermic reactions for a particular reaction, because every reaction pair, when you have a forward and reverse, one of them is going to be endothermic and the other one is going to be exothermic. And based on that, you can see which way the reaction will shift when you change the temperature. Changing the temperature has a larger effect when activation energy is large. And we saw it in this graph where our activation energy is like very at the far end. And when you don't have enough molecules that already have that activation energy, there's a bigger change when you change the temperature. And the K for endothermic reaction changes more than the K for exothermic reaction. Again, we saw it in this graph where we saw the difference between like having only a little number of molecules that already have the enough energy versus having already enough molecules that have the activation energy. The next thing is the reaction quotient. This is an expression describing the amount of product or reactant at a non-equilibrium state. So at any time, you can find the Q, but to get to K equilibrium, you have to be at equilibrium. And this is calculated the same way as K equilibrium. So it's like the concentration of products divided by the concentration of reactants. And compared to K equilibrium, you can compare this number to K equilibrium to predict the direction the reaction will proceed in order to reach equilibrium. So what possibilities do you have? You can basically have Q is equal to K. So at that point, you know you're at equilibrium. What happens if your Q is smaller than K? Well, Q is written as the concentration of products divided by reactants, right? If this number is too small and you want to make it a bigger number, what are you going to do? Raise the concentration of products and decrease the concentration of reactants. And if it's the other way around, if your Q is too big of a number and you want it to be smaller to get to equilibrium, again, what can you do? You have to change the denominator, you have to increase the denominator, and you have to decrease the numerator. So you will make more reactants and use more products. And when you disturb an equilibrium, what changes is Q. You're no longer at equilibrium, but the numerical value for K equilibrium will not change. So when you introduce a stress into the system and you see a change, you need to talk about Q and K when you get back to equilibrium. And I think one of the last things is the Le Chatelier's principle. Le Chatelier's principle basically tells you that when a reaction is at equilibrium, when a reaction at equilibrium is stressed by a change in conditions, the equilibrium will be reestablished in such a way to counter the stress. So the stress may be changing in temperature. We already talked about this. You can change the pressure, you can change the volume, which can change the pressure density, you can change the number of moles. And we're basically saying if the pressure is increased, what can you do? You can go to the side of the reaction where you have less gas molecules because that's going to decrease the pressure. Or when you increase the number of moles of something, you want to use those extra moles up so you can get back to equilibrium. And there are things that do not introduce stress into the system. A catalyst will never introduce a stress because catalysts only affect the rate of reaction and not the concentration of products or reactants. So you will still get to the same concentrations. It's just that you will get there faster. And if you put an inert gas into a system, inert gases are not gonna react because they're inert. So they're not gonna change anything in your reaction system. And the pressure that's introduced by the inert gases is not important. That's not a stress in the reaction. So when the equilibrium is disturbed, there are different ways to talk about it. You can check the Q and the K and see if they're like small, if the Q is smaller than or bigger than K, or if it's equal. You can use Le Chatelier to explain when a stress is introduced, what's going to happen, or you can evaluate the rate or rate of collisions. So you go into a little bit more detail of what happens on a molecular level. So for example, you can say if you decrease the volume of a system, the molecules will be closer to each other. Is that going to affect a unimolecular reaction where only one molecule is reacting? Not necessarily, but it's going to affect the rate of a bimolecular reaction where two molecules are reacting, because when you're more confined, when your volume is smaller, they're going to be closer to each other. So there's a greater chance that they will like hit each other and start reacting. So rate depends on probability of collisions related to density. And it's important for you to like read the questions very carefully and see which one they're asking for. So if the question is asking for Le Chatelier, you don't need to go into rates. But if the question is asking you to evaluate rates of rate of collisions, you cannot just say there's this stress, so the reaction shifts to this way. That would not be enough of an explanation. So always go and check what the question is asking for. And okay, we have the Rice tables. So we have seen the Rice tables before in the last semester, but if you haven't, that's okay. We've also done them this semester. The Rice table is going to be the reaction and the initial conditions, C is for change, and then the equilibrium amounts. The Rice tables can tell you amount of products or reactants related to stoichiometry and equilibrium constant. So what you need to do when you have a Rice table is to look at the stoichiometry for the relations in change. So if you have like 1 mole of product, 1 mole of reactants going into 2 moles of products, if you use X amount of this, you will make 2X amounts of reactants. And you should be cognizant of your units. So are you given concentrations? Are you given pressures? And another important thing with Rice tables is that sometimes you may have a solid in the reaction or a liquid in the reaction, which doesn't necessarily show up in the K equilibrium or Kc, right? Because they don't have concentrations, they don't have pressures. But they're still being used up or made in the reaction. And you should use moles to see what's going to happen to their relative amounts. And you should use the changes in the solids and liquids to see what's going to change in the gaseous and aqueous species. And after you get the equilibrium concentration or moles or pressure or whatever of like everything, and if you have liquids or pure liquids or solids, you will probably use this table in moles. When you get the initial equilibrium moles of everything, you can then go back to your equations and turn those moles into either concentrations or pressures, and then put them in the K equilibrium. So that's important. And I think that was the last thing, this part.
Yep, it's my turn, but sorry, that slide you were just on didn't look like the newer version of it. Could you go back to it?
This one?
Yeah, okay, here we go. That's the right version.
Yeah.
Okay, great. Okay, so I'm going to be talking about vapor pressure and phase transitions and phase equilibrium. So I'm going to start with just a definition of what vapor pressure is. So vapor pressure is the pressure of a gas above its liquid phase. So it's like the liquid phase transitions to the gas phase. What's the vapor pressure of the gas phase? And it's going to be constant at equilibrium. So at equilibrium, the rate of condensation of the gas molecules condensing into the liquid and the rate of evaporation, so the water molecules evaporating into the gas, is the same. So we're not expecting the relative number of gas molecules in the gas phase to change, and we're not changing the volume. So N over V is the same. So we don't expect the pressure to change when we're at equilibrium, and those two rates are the same. So one thing that's important to note is that your vapor pressure at a given temperature is going to depend on what the identity of your liquid phase is, so what the molecules are in the liquid phase. And that's because in the liquid phase, if you have stronger intermolecular forces, then it's going to take more energy to overcome those intermolecular forces and for the molecules to be able to escape to the gas phase. So you'd expect that for a liquid phase where you have stronger intermolecular forces between the molecules, you'd expect to have a lower vapor pressure, because at a specific temperature, fewer of those gas molecules would have enough energy to be able to escape into the gas phase. So you'd expect to have a lower rate of evaporation for that reason. And because rate of evaporation equals rate of condensation at equilibrium, then that lower rate of evaporation at equilibrium means you're going to have a lower rate of condensation as well. So you'd expect to have a lower vapor pressure as well than if you had molecules that have weaker IMFs at a given temperature, because weaker IMFs mean more of them will have enough K kinetic energy to overcome those IMFs and escape to the gas phase. So hopefully that made sense. Then moving on to the next slide. Thank you. So the main factor that affects the rate of condensation in your liquid phase equilibrium is the frequency with which gas molecules collide with the surface of the water, because the only thing, or of the liquid, because the only thing you really need to be able to do to condense into the liquid phase is for the gas molecule to hit the surface of the liquid. So how fast you're able to do that depends on how many molecules you have near the surface of the liquid at a given time, and that's going to increase with increasing density of the gas. Then the main factor that affects the rate of evaporation is your temperature, because just as we discussed, if you increase the temperature, you increase the fraction of molecules that have enough kinetic energy to overcome the IMFs and escape to the gas phase. So if you have higher temperature, you expect a higher rate of evaporation. Then I want to talk a little bit about our syringe example, and then I'm going to talk about boiling, because I feel like both of them are, if you can understand those, you understand this concept super duper well. And there's like complexities there that you don't necessarily see at first. So I'll start simple. We had in class a demonstration with a syringe filled with water, and we pulled it back and then fixed it there so that the vapor pressure was able to exist above the water. And we measured the pressure of the vapor phase above the water as we changed the volume. And we found that as we changed the volume, the vapor pressure didn't change. So now I'm going to walk through why this is while talking about rates of condensation and evaporation. So instantaneously, when we increase the volume, because we haven't changed the number of molecules in the gas phase, we have N over V, and V is going to be greater. So we expect to have a lower density. So this means at a given time, there's less gas molecules near the surface of the liquid. So we expect the rate of condensation to go down. We've lowered the density, so we expect the rate of condensation to go down when we increase the volume. Now, if the rate of condensation goes down, this means that now our rate of condensation is less than our rate of evaporation. So we expect more molecules to be condensing than evaporating. So you expect the number of molecules in the gas phase to decrease. Now, if we're decreasing the number, sorry, I got that backwards. The rate of condensation is less than the rate of evaporation for the reasons I just described. The density goes down. So now if the rate of condensation is less than the rate of evaporation, you expect more molecules to be evaporating than condensing. So you expect more molecules in the gas phase. So then your rate of condensation is going to increase again until the two rates are equal again. Sorry for getting that backwards. So yeah, more molecules evaporating than condensing, more molecules are going to go into the gas phase. The gas density goes up again until once again, the rate of condensation and evaporation are equal. Does anyone have any questions on that? Because I got that backwards at one point. I don't want to confuse anyone. So if you have any questions, just type them in the chat or raise your hand. Okay, then I think we'll move on to boiling because it's a little more complicated than you think it's going to be. Oh, sorry, I got a question. Changing the concentration doesn't change the pressure either. No, okay, so the only thing that will change the vapor pressure at equilibrium is changing the temperature. And the reason for like a given liquid, because we talked about if you change the identity of a liquid, then you expect a different vapor pressure at a given temperature. But for a given liquid, the only thing that's going to change the equilibrium vapor pressure is temperature. And the reason why it's only temperature is you can kind of think that, okay, the equilibrium constant is the rate of the forward reaction over the rate of the rate constant for the forward reaction over the rate constant for the reverse reaction. And it's also the concentration of products at equilibrium raised to their molar coefficients over the concentration of reactants at equilibrium raised to their molar coefficients. And if we're looking at Kp, then instead of concentrations, we're looking at partial pressures. Okay, now if we change the temperature for the reasons that Golnahal just discussed, we change Kq, right? So if we're changing Kq, and if Kq is equal to the concentration of products over the concentration of reactants, then we expect the concentration of products and reactants to change, and that can only change if we're changing the vapor pressure. So just to condense that all, because changing the temperature changes the equilibrium constant, it also changes the vapor pressure. And to think about that more conceptually, when we increase the temperature, we're going to increase the rate of evaporation, right? Because more molecules have enough Ke to overcome the IMFs. So if we're increasing the rate of evaporation and at equilibrium, the rate of evaporation and condensation are equal, then we must also increase the rate of condensation. So both of them are going to be higher at equilibrium and we'll have a higher vapor pressure. But if you change anything else, if you change concentration, if you change volume above a liquid, we don't expect it to change. And a faster way to see that conceptually is if we increase the volume above the liquid, we haven't changed the temperature at all, right? So we haven't changed the rate of evaporation. And because at equilibrium, the rate of evaporation and rate of condensations are equal, if we haven't changed the rate of evaporation, then we can't have changed the rate of condensation at equilibrium. So we don't expect those to change. And someone asked, why does rate C go up again? I think that's rate of condensation. So, okay, I'll walk through it slowly one more time. So you have syringe, it has liquid and it has gas over it. Now I'm going to increase the volume above the syringe. So now I've increased the volume, I've decreased the density of the gas molecules above the liquid phase. So fewer of them are colliding with the surface of the liquid at any given time. So the rate of condensation goes down, but I haven't changed the temperature. So the rate of evaporation has not changed. So now the rate of evaporation is greater than the rate of condensation. So more molecules are evaporating at any given time than they're condensing. Okay, so this means that if more molecules are evaporating than condensing at any given time, I'm going to increase the number of molecules in the gas phase. And when I increase the number of molecules in the gas phase, I'm increasing the density of the gas, which means, again, there's going to be more gas molecules at any given time near the surface of the liquid than there was before. I'm going to have a higher frequency of collisions. So as I increase the number of molecules in the gas phase, I expect the rate of condensation to go up again. And it's going to keep increasing once again until the rates are equal. And that's when we have as many gas molecules evaporating at any given time as I have as many liquid molecules evaporating at any given time as I have gas molecules condensing and then I've reached my equilibrium point, and the vapor pressure is going to be the same as it was before, which again makes sense because we haven't changed the rate of evaporation because we haven't changed the temperature. And then Olivia said, so then does the rate of evaporation / condensation increase in total but are still equal? Not in this case. So in this case, we haven't changed the temperature. And so like in this example, at first, when we increase the volume, we decrease the rate of condensation. And when it increases again, it just reaches the point it was at before. So we haven't actually changed the rate of evaporation or condensation at all overall, which again makes sense because we haven't changed the temperature. So we can't have changed the rate of evaporation. So they don't increase in total. In terms of the temperature example, then at equilibrium, if we increase the temperature at equilibrium, both rates are going to be equal again, but they're both going to be higher than they were originally, because when we increase the temperature, we increase the rate of evaporation, and at equilibrium, the two have to be equal, so the rate of condensation must increase as well. I hope that makes more sense. I feel like I repeated myself a lot there, but if I'm going too fast or if I can clarify something, let me know, because I feel like this is cool stuff and I want to be able to explain it clearly. If I remove some water from the system, then that would change equilibrium, right? No, it would not. Or the equilibrium vapor pressure. No, changing the relative amounts of liquid and gas. If you got rid of all the water entirely, then yes, because you wouldn't have phase equilibrium anymore because you just have a gas. But if you only got rid of some of the water, it wouldn't, because it's easier to explain with the gas phase, but with the liquid phase, the way I would say it is you haven't changed the amount of liquid molecules at the surface, at like the interface of your soliding of your gas and liquid. So you haven't changed the rate of condensation at all, because you're going to collide with the surface of the liquid just as often. You haven't changed the density of the gas above the liquid. So at equilibrium, the rate of evaporation and condensation can't have changed it. Also, if you remove water from the system, you haven't changed the fraction of water molecules that have enough Ke to overcome the IMFs and evaporate. So you actually wouldn't expect to change the rate of evaporation at all. The thing that might change it is if you change the surface area, because if you increase the surface area of like the liquid water interface, then you'd have more water molecules near the surface. So then they could like evaporate more easily when they have enough Ke. But if you just like take water from your system, you want to change that. And actually, even if you like change the surface area, the vapor pressure won't, sorry, I know it's going into too many details. You probably won't be quizzed on this on exam. But if you change the surface area, you won't change the vapor pressure, even though you'll have a faster rate of evaporation, because you'll also have a faster rate of condensation. Someone said, I'm kind of confused as to why decreasing the volume doesn't ultimately increase both rate of evaporation and condensation. I understand why pressure stays the same though. Okay, so the main factor that affects the rate of evaporation is temperature. So if we're not changing temperature, we're not changing the rate of evaporation. So decreasing the volume of the liquid decreasing the volume of the gas above the liquid shouldn't change the rate of evaporation, because we haven't changed the temperature at all. If you're confused about like ideal gas stuff, like you saw that PV equals nRT, and if we decrease V, then we increase T, that's not applying here, because the ideal gas law is just for the gas phase. And here we're talking about the liquid and the gas phase. So you can't use that argument here. So if you thought that like decreasing the volume changed the temperature, that's not the case here for the liquid phase. So we can't have changed the rate of evaporation. Any more questions? Got it. Okay, awesome. I'm so glad. Then boiling points. We'll get to that next. Thank you. Okay, so boiling is like the most exciting thing for me, because like a bit of the reason why I was excited to be a TA is like understanding boiling better, because for the past 4 years, every time I make pasta, I would like stare at the pot of water boiling, and I'd realize that like I didn't completely understand what was going on, and like I really wanted to understand, and now I understand it. So hopefully I'll be able to convey that to you guys. So we've discussed in class that water, or like liquid gas equilibrium, liquid's always evaporating to gas. Like for water, we always have like the liquid and gas phase at equilibrium, even when we're not at the boiling point. So we can evaporate like liquid to gas at essentially any temperature. So what's special about the boiling point then? Like what physical process do we see at the boiling point that we don't see at other temperatures for a pot of water, even though liquid and gas is always evaporating? I want someone to answer this. Like what do we see at the boiling point? Yes, McKenna.
We see like the water bubbling.
Yes, bubbles. Yes, exactly. Sorry, I get excited about that. So can someone tell me why are we able to see bubbles at the boiling point, but not at other temperatures? Or maybe I'll go into it. Okay, so the reason why we can see bubbles at the boiling point and not at other temperatures is because at the boiling point, the vapor pressure, so the pressure of the gas molecules coming off our liquid, are equal to the applied pressure, which is just like atmospheric pressure if we're just like cooking a pot of pasta. So what this means is that in your bubble's made of gas molecules evaporating into the liquid phase, right? So the pressure inside your gas bubble is equal to the vapor pressure. And then the pressure pushing in on your gas molecule, or sorry, the pressure pushing in on your bubbles equal to the applied pressure. So when the vapor pressure equals the applied pressure, then the pressure inside your bubble equals the pressure outside your bubble, so the bubble can exist. And that's why you have bubbles forming at the boiling point, but not at other temperatures, because at other temperatures, the vapor pressure will be less than the applied pressure. So atmospheric pressure causes your bubble to just collapse because there's not enough pressure inside the bubble to sustain it. So that's what's special about the boiling point, is the fact that the pressure inside the bubbles equals the pressure outside the bubbles, and your bubble can exist and you see bubbles. And so this graph that I have up here is just showing how your boiling vapor pressure changes with applied pressure, because your boiling pressure is going to be whenever, like we just discussed, your boiling pressure is whenever the vapor pressure equals the applied pressure. And one thing that I find just mind-blowing is usually when you think of like boiling, you think of the idea of like needing to increase the temperature and like boiling for water only happening at 100 degrees Celsius. But in our syringe example that we saw in class, we actually caused the water to boil without changing the temperature at all. And the way we did this is, okay, so we have, I wish I had like the drawing in front of me, but I'll try to do it with words. So we have the syringe and it's filled with water and we don't have any gas phase above it. Then we pull back the syringe and instantaneously the applied pressure, which is going to be like what's above our liquid phase, the applied pressure is 0. It's just a vacuum, right? Because we pulled back the water and there's nothing above it. So we have 0 external pressure. Then that means that the vapor pressure, so the pressure of the gas molecules coming off the liquid, has to be greater than the external pressure, because the external pressure is 0, because we just created a vacuum. So you see the water start to bubble because the pressure inside the bubbles is greater than the pressure outside the bubbles, which is just 0. So that's why you see bubbling. And then the bubbling stopped at the point where we created enough gas molecules that now the external pressure equals the vapor pressure, and the bubbles are just there, but they're not like bubbling really fast. So that's something interesting. Now, another thing is, why is it that, oh, actually, wait, I'll ask this question after. So yeah, this graph is just showing how if you change the applied pressure, you change the vapor pressure of the vapor pressure of the gas at the boiling point. Because yeah, if you have a different applied pressure, you're gonna have a different boiling point, because the boiling point is where the vapor pressure equals the applied pressure. Sorry, I just thought I got a question. Is the applied pressure the pressure due to the liquid? No, the liquid factors in a little bit to the applied pressure, but pretty much, what's the word? Negligible, like very, very, very small. The applied pressure is more like the pressure of the atmosphere. So when you have a pot with water in it, the applied pressure is like the pressure of like the atmosphere, all the gases in the atmosphere. And the vapor pressure is the pressure of the gas molecules of water going into the liquid phase. So that's the difference there. You're welcome. Then one thing I want to do before moving on, oh, I should have prepared this better, is talk about something that shows up in the CDS, which is like the idea of when the vapor pressure is equal to the applied pressure, the vapor is able to sustain itself in a syringe. So I drew a little diagram that kind of shows this. So So we have water with gas above it, and we have above it a movable piston. So it means the piston can move up and down. So in this example, the external pressure is the pressure from the atmosphere pushing down on our liquid and gas phases, and the vapor pressure is the pressure of the liquid above, or sorry, the gas above the liquid phase pushing upwards. So something like, to make the external pressure maybe make a little more sense, is like if we put a few grains of sand on the piston. So the external pressure is the force pushing down on our liquid and gas phases, and the vapor pressure is from the pressure of the gas molecules, and that pushes up on our movable piston. So if the external pressure is greater than the vapor pressure, like in this example, then the downwards force is going to be greater than the upwards force, and the piston's just going to move down until there's no gas molecules anymore. There's only liquid. Similarly, if the vapor pressure is equal to the applied pressure, then the upwards force is going to be greater than the downwards force, and the piston's just going to move up until the two forces are equal again. And if you're at equilibrium, if the external pressure equals the vapor pressure, then the two forces are equal, so we're not going to change at all. So a complexity about this is, in our example with the pot of water, we have it on the stove, and we know that water is evaporating even though the two pressures are equal. So how is it that we're able to have a vapor pressure when we have an external pressure that's greater than the vapor pressure? And the difference between the two systems, the difference between like my pot of water on the stove versus like this piston or syringe example that I drew, is that this is a closed system. This is a completely closed system. So all the gas molecules are like locked into place. And if I have a greater pressure, then I can push them all down. But in our pot of water, it's an open system. So whatever gas molecules evaporate, they're able to like go and escape and be free. So that's the difference there. That's how we're able to have equilibrium between the gas and liquid phases for our open pot of water, even when the external pressure is greater than the vapor pressure. Can you hold the sheet up again? Yes, I can. And would it be possible to send a picture of the drawings? Yes, when Heather's presenting, I'll take a photo and I'll send it in the chat. So Sachi, hopefully I don't need to hold it up because I'm going to be sending a photo. Okay, next slide. Phase transitions. Okay, so a phase transition is just the change between a gas, liquid, or solid phases at a specific temperature and pressure. And the boiling point is when we have a transition between the liquid and vapor phases, or sorry, let's say liquid and gas phases. And the freezing point is the point where we transition between the liquid and solid phases, which will be the same as the melting point, which is when we transition between the liquid and the solid phase. And then we have a graph of phase transitions. And this just shows how the temperature at which we make our transition between one phase and the next depends on the applied pressure. So that pressure on the y-axis is applied pressure. So something that like tripped me up actually at the beginning of the semester was trying to apply this to the example of an open pot of water on the stove, because I was like, wait, if I'm at like 50 degrees Celsius, I'm going to have both liquid and gas molecules in my pot of water, even though I'm at 50 degrees Celsius and atmospheric pressure, which is like 1 atm. So according to this graph, it looks like I should only have liquid, but I know I have liquid and gas. And again, that's because this is for a closed system. So this is for if we're like this and all the gas molecules can all be like pushed down because it's closed. When we have a greater external pressure, if we have our open pressure, our open system, then the gas molecules can escape wherever. There's no way to like keep them contained and push them back down. So yeah, this is for a closed system. So if you ever get confused, you can just remember that. So the y-axis is external pressure and the x-axis is temperature. So this is the phase diagram for water. And the way I can tell that just by looking at the curve between the solid and liquid phases is the fact that the curve goes like this. It's like a negative slope. And what that means is that the density of the solid is less than the density of the liquid. If they had the same densities, then this would look at like a straight line. And you can actually see that at the critical point. I don't think we covered in class, so I doubt that they'll ask you about this on an exam. But at the critical point, the densities of the gas phase and the density of the liquid phase are equal, so you can't distinguish between them. And you can see like there's a vertical slope at that point. So going back to solid and liquid, there's a negative slope, which means the density of the solid is less than the density of the liquid. If it was a positive slope, then the density of the liquid would be greater, or sorry, the density of the solid would be greater than the density of the liquid, as it is for most other substances. And what's special about the density of the solid being less than the density of the liquid for water is it means that you can actually melt ice only using pressure. Because if you have a smaller density in the solid phase than the liquid phase, as you add pressure and like the molecules are being squished together, you can put them into the liquid phase, which is cool. You can't do that for other substances. And I think that's everything. Oh, sorry. Can you please go over supercritical fluid? It was on one of the homeworks. Okay, I can try. I'm actually not an expert when it comes to it. So that's going to be the point. All I can say is that's the point where the density of a liquid phase is equal to the density of the gas phase. And because the densities are equal and you're like talking about the same molecules, it's hard to distinguish between which is which. It's been told to me that they look the same at that point, but I don't really know more beyond that. So I hope that helps. And then someone said, can you determine the boiling point without being given it? Yes, you can, because if you're given the applied pressure, then you know that the boiling point is going to be equal to whenever the vapor pressure is equal to the applied pressure. So you can look at Golden Hall, could you go back to that graph of this one exactly? Okay, so if I know my like applied pressure is 400 torr, I can look at this graph and I can see where the X value is for 400 torr, and that tells me when what the temperature is at 400 torr, and I know that the vapor pressure is going to be equal to 400 torr at the boiling point, so I can use that to figure out the boiling point. I hope that helps. Okay, then this heating curve. I feel like we didn't cover this in class, but I kept it just in case. So this just shows how the temperature of your substance changes as you add heat to it. And I think like the main thing to note about this is you'll see that at the melting and boiling points, when you add heat to your substance, you don't change its temperature, right? And the reason why that is like all the energy from the heat is going into making the phase transition. So overcoming the IMFs, for example, from the liquid to the gas phase, and none of it's going to changing the temperature. So that's the only thing to note about this, but I feel like we didn't cover it in class, so I wouldn't worry about it too much. Any more questions before we move on? Okay, it doesn't look like it. Sorry guys, sorry other TAs, I feel like I took too long there.
All right, we can go to the next slide. Okay, awesome. So I'm just going to talk briefly about entropy and the second law of thermodynamics. So this is pretty much material that we've covered in this past week. So it's pretty recent, starting with favorability in microstates. I think that was introduced on Monday's lecture. But essentially, we know that when we're not at equilibrium, the system will always try to spontaneously go to that equilibrium state, whether that be reverse or forward. It just depends on what point we're at relative to that equilibrium point. Also, in terms of microstates, so we define that in class as thinking about the differences in like position, not only position, but like anything that characterizes these different like molecules or atoms. So you can think about it in like velocity, like kinetic energy, everything that's like that could be variable in different microstates are different variables in here. So like locations, motions, a bunch of other things, actual arrangements in that sequence. And it's important to recognize that with different microstates, each microstate in itself has the same probability, but each macrostate does not occur with the same probability. And I'll talk a little bit more about that in the next slide. But another point to this is that we have more disordered states than ordered states. Just think about how many ways you can mess up your room versus having your room completely clean. And then next slide, please. All right. And so a little bit more about entropy. So I was kind of introducing this in the past slide, but why is there not a contradiction between the equal probability of all molecule arrangements and the overwhelming possibility of the final mixed state? So that's kind of distinguishing between the probability of our individual microstates versus our macrostates. So a specific arrangement, whether you have like all your molecules in one arrangement or another, those are microstates. But then a macrostate is looking as a whole, like, is it ordered? Is it disordered? So for example, like if you have a drop of water or a drop of colored water in a glass, for instance, if your entire water glass becomes like blue, that's like disordered because that little drop of blue dye that you put in has now spread everywhere. And no matter how those exact molecules have kind of spread around, the overall thing is blue. So that's what you see as that macro state. And so the probability of observing a particular macro state is proportional to the number of microstates with that macroscopic property. So that's looking at the Boltzmann equation here, where W is the number of microstates, K is the constant, and then S is the entropy. And another way that helped me to think about macrostates and microstates are like, I think in Kincaid's section, at least she brought up a dice example. So if you think about, you have two dice and you're thinking about like rolling a 7 versus rolling a 2, for example. In one situation, in a microstate kind of example, the probability of rolling like both of your dice as 1 and 1s versus like 2 of your dice as 3 and 4 are equally likely. But those are microstates. If you think about macrostates, there are more combinations of these two dice to make a 7 versus making a 2. If you want to roll a 2 with those dice, you have to have a 1 and a 1. But if you're trying to get to a 7, you can have a combination like 1 and 6. You have a combination of 5 and 2, things like that. So there's just more microstates for that macrostate of 7 than there is for a macrostate of 2. And if anyone has any questions at any point, please do comment or raise your hand as well. And then a little bit more here. So in terms of the random motion of molecules, molecules don't know where to go. They're just moving randomly. So things usually just happen because it's the most probable state. And so that's why we see mixing. Technically, molecules don't want to be, like they don't know anything, like they're just kind of moving around. But I have a quick question, let me just double check. The K in the Boltzmann formula. I do not have that number at the top of my head, but usually constants are given on exam if not mistaken. But if not, just go back and double check the slides. It should be on the slides. Oh. And then, all right, and then back to here. And also if I accidentally miss your question, I'll make sure to get back to it at the end. It's just a little hard for me to toggle all my windows. All right, and then in terms of a little bit more, back to mixing. So it occurs spontaneously because there's just way more arrangements of having mixing occur than having that like one drop of blue dye stick together while it moves around that whole like water glass or anything like that. It's more likely to kind of spread around and disperse just because it's the most random. And so from that, you can kind of conclude that a spontaneous process occurs because it is just the most probable final state. And then next slide, please. Great. And so this was the example I was alluding to in the past couple of slides, but yeah, if you drop some dye into water, it'll disperse throughout the entire glass. It doesn't know that it wants to do it, it just does because it's just always moving, and that's the most probable thing for it to happen. And so this process is spontaneous and irreversible as well. It's just more likely for them to be completely spread out than decide to at one point clump all back together again. And then again, yeah, a spontaneous process occurs because the most probable final state. And then next slide. Yes, perfect. And so this table is basically kind of a summary. It's not completely comprehensive, so I would definitely recommend checking your notes for all of the different trends that we see in entropy. But if you're looking at that left side over there, like absolute entropies of specific substances, that table, you can see how looking at like different phases like solid, liquid, and gas, we see differences in entropy if we look in that third column of S. And we can also see like between different molecules, what kind of trends we observe. So that's also kind of covered in that table right next to it on that right side. So solid, liquid, and gas, we know that gases always have highest entropy because it just has the greatest degree of motion and a lot of variety in how molecules can be positioned, their speed, all of that thing. And then same thing, liquid has more entropy than a solid, same reason as why gas has more than a liquid. And then entropy also increases with increasing temperature. The reason for that is just there's a lot greater range of like momentum. There's it moves around a lot, so there's just a lot of ways to distribute the energy amongst these molecules. So that also adds to the greater entropy. It's important that entropy is not only dependent on position, but a bunch of other factors as well that describe a molecule. And I just got a question. Could you go over why larger molecules have higher entropy? Yes, I was just going to get to that point. So great question. So that kind of covers in part 4 if you look at that table. But the entropy of substances with more atoms is greater than substances with fewer atoms. So larger molecules, for example, like if you have a molecule that's like C4H10 versus like CH4, the greater size molecule C4H10, think about like how many ways you can kind of, if I built like a, if I had like a molecular modeling kit and I could build it for you, there's a lot of ways I can kind of move the bonds around, versus methane, which is like trigonal planar. There's not much I can do with that in terms of like moving things around. So if I have like C4H10 and I can like move the bonds around a lot of different positions, that adds to the overall greater entropy. And additionally, that question also covers like part 5 of this table, which is substances with higher molecular weights have higher entropies than substances with low molecular weights. So not only with C4H10 do you have like a lot of variety, you can move those bonds and that adds to entropy, but also the fact that C4H10 is heavier than methane. So the molecular weight is also a factor. And the reason for that gets into like quantum mechanics a little bit. So I wouldn't worry about like having to actually provide an example. I mean, to actually provide a reasoning, I think just kind of understanding this trend is enough. But if you're curious, it can be simplified to just a little bit of thinking about momentum. If you have something that has a greater molecular weight, think of it as having a greater range of potential momentum like sizes. So you can think of like C4H10 as having like a greater range, so maybe like a wider curve, versus like CH4 methane having like a narrower range of momentum. So having that greater range of momentum with that bigger molecule adds to more entropy as well, because momentum can also be one of the factors that can increase entropy. All right, and that is all from this slide as well. And next slide, please. All right, and I believe this is the last slide. So a little bit about condensation and freezing. So a spontaneous process does not necessarily always produce the final state of greatest probability / entropy. So you might think, what's up with that? It's important to also consider like the delta S of your surroundings and thinking about heat flow. It is true that like if you have an isolated system, you can just focus on the system itself and see the change in entropy. Or if you were just looking at the whole delta S of the universe, you can then see that both of those have to be positive for any spontaneous process. But because phase transitions include like changes of energy with heat flow, you have to be able to consider that as well. So that can be something that you need to remember if you see something that logically you're like, oh, why does the process happen, or why doesn't the process happen? Think about the overall what's happening in terms of where things are going and what is affecting what. And I believe this is the last slide. Yes. So we are open to questions. If anyone wants to like go back, or if they missed a slide, we're more than happy to go back for you to ask your question, or just to like take notes on the slide as well. But y'all are free to go if you don't have any questions as well. And we have a bunch of review sessions.
Wait, sorry, I have another set of slides for Delta G.
Okay, awesome.
I'm sorry, you have to hear my voice again. I already talked too much, but yeah, there is more material, so don't leave yet. Unless you don't want to hear about Delta G, which is your choice, but since you'll need it for the exam, you might want to hear about it. But if you have any questions on like Heather stuff, I'll mute myself and I'll wait. I'm gonna assume no more questions on that next set of stuff. Okay, so now we're gonna cover delta G. So first of all, oh, sorry, Golden Hall, if we could change slides, that would be great, thank you. First of all, we're gonna talk about where we get delta G from. So the idea behind how we got delta G is that for spontaneous processes, delta S is positive. So for all processes, delta S of the universe has to be greater or equal to 0. But in this class, we don't really look at any processes where delta S of the universe is equal to 0. So we say for all spontaneous processes, delta S of the universe has to be greater than 0. Then delta S of the universe is equal to the change in entropy of our system. By the way, this is like all detailed stuff. I really highly doubt they'll ask you about it on an exam. I just want to go a little bit over the derivation we did in class. So delta S of the universe is equal to the sum of the delta S of the system plus the delta S of the surroundings. And we can say that the delta S of the surroundings is equal to the heat flow into the surroundings, which can be represented by delta H. So we can say it's negative delta H of the system over T, and then putting that back into our delta S of the universe equation, we get delta S of the system minus delta H of the system over T. And we say that this has to be greater than 0 for any spontaneous process. We can group this all together with the term delta G, which is change in Gibbs free energy, which is delta H minus T delta S having to be less than 0 for any spontaneous process. So I know like that didn't really make sense, and that's because I didn't really go into like the concepts behind it, like why we can say delta S of the surroundings is negative delta H of the system over T, but you're not going to be asked about this. So this is just to show how like delta G gives you a combination of delta H and delta S. And it's also important to note that the delta S in this equation is delta S of the system. It's not delta S of the universe. We got this idea of Gibbs free energy from delta S of the universe needing to be positive for a spontaneous process, but the delta S in this equation is a delta S of the system. So that's why like you can have negative delta S of the system, even if you can't have negative delta S of the universe. Then moving on to the next slide. Okay, so the sign of delta G tells you which direction the reaction is going to proceed in for you to get to equilibrium. So if delta G is negative, then the reaction is going to be spontaneous in the forward direction. If delta G is positive, then your reaction is going to be spontaneous in the reverse direction because you need to move in the reverse direction to get to equilibrium. And if delta G equals 0, we're at equilibrium. So now I'm going to struggle and try to annotate this. Just changing my color. Okay. So delta G can be calculated at any point in our reaction under any conditions. So let's say I'm at this point in my reaction. So at this point I have more reactants than products, and I want to know what delta G is. This is a curve of G versus the reaction progress. So delta G is just going to be the slope of this curve. So here is delta G. I'm not going to, actually I will. Delta G. And delta G here is negative. And like we said earlier, if delta G is negative, that means the reaction is going to be spontaneous in the forward direction, which means we have to move in the forward direction to equilibrium, which is over here. And I can also draw arrows here. At any point here, I'm going to get a negative delta G, which tells me I need to move in the forward direction to get to equilibrium, at which delta G equals 0. Now, similarly, if I calculated delta G at this point in my reaction, I would get a positive delta G, which tells me that I need to move, which tells me that the reverse direction is spontaneous and tells me that I need to move in the reverse direction to get to equilibrium. So at any point here, I'm going to get a positive delta G, a positive slope, which means that the reverse direction is going to be spontaneous and I'm going to move in the reverse direction to get to equilibrium. So summed up, delta G tells me which direction is going to be spontaneous, the forward and reverse direction, which tells me which direction do I need to move in to get to equilibrium. And if delta G is negative, then it means the forward direction is spontaneous. And if delta G is positive, it means the reverse direction is spontaneous. Then now we're going to discuss on the next slide the concept of standard free energy. So the first thing, sorry, oh no, what do I do? Okay, I can just click clear. That sucks that it's not going to stay there though on the other side. I was hoping it would. So delta G naught. So what this naught symbol indicates is standard conditions. So delta G naught is delta G of my reaction when I have 1 atm pressure and 1 molar concentration of all substances. So 1 molar concentration of products and 1 molar concentration of reactants. So delta G naught is the change in Gibbs free energy from my reaction, only at standard free energy. So one thing that's important to note is like, rarely in our reaction do we get to a point where we have like 1 atm pressure and 1 molar concentration of all substances. So delta G naught doesn't really tell us across like the whole reaction. It only tells us at like this one specific condition, what's the sign of delta G naught going to be. And the usefulness of delta G naught, since it's weird that it's useful even though it doesn't really happen in our reaction very often, because it's not often that we get 1 molar concentration of everything. The usefulness of delta G naught is it tells us favorability of the reaction. So delta G tells us spontaneity and delta G naught tells us favorability. And the way that I like to think about favorability is literally just at equilibrium, am I gonna have more products or more reactants? That's all that delta G naught tells you. At equilibrium, am I gonna have more products or more reactants? And then our equation from before, delta G equals delta H minus T delta S. If we're at standard conditions, then instead of saying, we can use like delta G naught equals delta H naught minus T delta S naught. Sorry, I see I'm getting questions. When you say delta G, which side is your starting G? If your final G is the G at that specific point in the reaction, is your starting G at reactants or products? Golna, how would you mind going back one slide? So delta G is the derivative, here. So it's like, if I was going to do like starting and final, this would be the starting G and this would be the final G. And then I do like the change in Y over change in X to find what delta G is. I hope that answers your question. So delta G is just, but delta means change though, right? Yeah, so it's the instantaneous change. It's the derivative of the curve. So it's like the instantaneous slope at any point along the curve. So it's not over the whole thing. It's like at the specific point in your reaction, what's the instantaneous change in G? I hope that helps. Yeah, instantaneous makes sense. Got it. Okay. There was another question. How the amounts can be different, but the concentrations have to be the same. Yeah, if we're talking about standard conditions, we just need like 1 molar concentrations of everything. Yeah, and that's delta G naught is when we have standard conditions. That little naught symbol, the little 0 symbol, that means standard conditions. And moving on to 2 slides forward, please. Oh, actually, sorry, 1 slide back. 1 more forward. Sorry. Perfect. Okay. Oh, wait. I think there was there one more in between?
I don't think so.
Okay, that's fine. This is good. Oh, the one with the curve.
This is okay. This is the one with the curve.
Mm-hmm.
So then this is the next one. I can go back and check them.
No, one more after this, please. Because I just want to illustrate like delta G naught and favorability. Okay. Now I'm going to annotate this. So here I want to illustrate my point about delta G naught tells us about the favorability of the reaction, and all the favorability being, all favorability means is, are we going to have more products than reactants at equilibrium? So hopefully this demonstration that I'm going to do with the curve will help. So the x-axis is the amount of reactants and products. And because of that, on the x-axis, we can place our equilibrium constants and our reaction quotients that show like the ratio of products and reactants. So when we're at equilibrium, oops, sorry, I'm not drawing even though I'm trying to, there we go. This is K. K is at equilibrium, right? It's our equilibrium concentration of products and reactants. So this is K on this graph. Now, we discussed that standard conditions is when we have 1 molar concentrations of reactants and products. So that means that at standard conditions, Q is going to be equal to 1, right? So because I'm just going to have 1 to the power of n for products divided by 1 to the power of m for reactants. Like it's just 1 to the power of whatever over 1 to the power of whatever. So Q is going to be equal to 1. So delta G naught on the x-axis, so it's 1 atm pressure and 1 molar concentrations. Wherever delta G naught is where Q is. So let's say this is Q. So then the slope of this curve at 1 molar concentrations and 1 atm pressure is delta G naught. So if Q lies to the left of K, that means that delta G naught is negative. And sorry, I should write Q equals 1, right? So if Q lies to the left of K, delta G naught is negative, which means that we have more products, a higher concentration of products at equilibrium than we do at reactants. We have more products at equilibrium than we do reactants. And it also, we can see that in terms of Q and K, because if Q equals 1 and K is greater than 1, that means that we're going to have more products and reactants at concentrations, right? More products and reactants at equilibrium, right? Like we saw earlier, if K is greater than 1, products are favored over reactants. If K is equal to 1, they're about the same. If K is smaller than 1, reactants are favored over products. So you can see that here. So we have K over here, we have Q equal here, we have Q over here, and the slope of delta G naught is negative, which means that equilibrium, we have more products than reactants. Similarly, for this curve over here, K is going to be here, and Q is still going to be here, Q equal 1. And the slope of delta G naught is going to be positive. And we see that when delta G naught is positive, there's going to be more reactants than products at equilibrium. So the reaction is going to line more towards the reactants whenever we have a positive delta G naught. Does this make sense? I know that like Q can be calculated at any point in the reaction, but I'm saying when Q equals 1, that's the X value that we find delta G naught at. That's what I'm saying here. And this is just to illustrate how delta G naught tells us about favorability. So if delta G naught is negative, we have more products and reactants at equilibrium. And if delta G naught is positive, then we have more reactants than products at equilibrium. So that's delta G naught. And delta G tells us about spontaneity, which is at any point in our reaction, which direction are we going to move in to get to equilibrium? So it doesn't matter what X value we use here. It means like at any point in the reaction, which direction do we move in to get to equilibrium? And then delta G naught tells us at equilibrium, are we going to have more reactants or products? So that's the difference between those two values. Yeah, and the main thing is delta G naught only at standard conditions, only at 1 atm pressure and 1 molar of everything. So if delta G naught is negative, the forward reaction is favored. Yes, you could say the forward reaction is favored because you have more products than reactants at equilibrium. Yeah, just because I find the idea of like favorability in general confusing. I guess you could say like the forward reaction is favored, and all that means is you have more products and reactants at equilibrium. So delta G naught to me gives you like two important pieces of information. It tells you at equilibrium, are we going to have more products or reactants? But it also can give you information that helps you calculate delta G. Those are like the two big uses of delta G naught to me. And yeah, it's important to like stress why is it useful, even though we like rarely get standard conditions during reactions. Because of that, it helps us calculate delta G, and it helps us figure out if we're going to have more products or reactants at equilibrium. So that relationship between delta G naught and delta G can be shown on the next slide. I think I showed that equation. Yeah, so these two equations just show the relationship between delta G and delta G naught and the reaction quotient. So in general, we can say that delta G is equal to delta G naught plus RT ln Q, but because at equilibrium, delta G is going to be equal to 0, right? Like that was the bottom of our curve. When we have the minimum G, we have a minimum, a local minimum. The instantaneous rate of change is 0, delta G is 0. So then we get 0 equals delta G naught plus RT ln Q, because when we're at equilibrium, Q is equal to K, right? So that's how we get that second equation. And the second and third bullet points there, like if delta G naught is less than 0, K will be greater than 0, that's greater than 1. That's what I just illustrated on the last slide. So if the equilibrium, if we have a negative slope, it means that equilibrium is to the right of Q. and Q is 1, so K is greater than 1. And if we have a positive slope, it means that equilibrium is to the left of Q, and Q is 1, so K is smaller than 1. And I think that's everything. Is there one more slide? Yeah, so this is just like, I won't go over this because it's not that complicated. It's just at what temperature will G be negative? At what temperature will delta G be negative? So just like to do one example for the last point, if delta H is 0, then delta G equals minus T delta S. So if delta S is positive, then we're going to get minus T times a positive number. So we're always going to get a negative delta G. That's all this is showing. And I think that's everything. This is like pretty complicated stuff. So if you guys have any questions, please like don't hesitate to send me a chat. Also, maybe this is like, I hope this like doesn't sound condescending, but like something that my middle school teacher told me is that if you have a question, half the class definitely has the same question, so you should ask it. And like I always remember that whenever I'm scared to ask questions, I'm like, okay, I'll do it for other people. Maybe it's selfish of me, maybe other people don't have the same question, but I just convince myself that other people do. So yeah, ask me questions.
So one of the questions I got a couple times is like the significance of Q is equal to 1. So Q is equal to 1 only happens at standard conditions, right? So your standard conditions are basically every species has a concentration of 1 and their pressures are also like 1 atm. And you have to be at 25 degrees Celsius. So Q is equal to 1 is at that specific like standard conditions, and your equilibrium is most of the time not happening at standard conditions. It's somewhere like random. And you can look at Q, and we have Q because like we can use this Q is equal to 1 standard conditions to find delta G naught. And delta G naught means that like little 0 means you're at standard conditions. And why do we care about this? Because we can then look at favorability of a reaction at standard conditions, which are pretty easy to like get to, because it's like 1 molar of everything, 1 atm pressure of everything, and like 25 degrees Celsius is something you can very easily like create in lab. So it's an easy way to like look at a reaction in lab, and that's why we have that specific value in addition to delta G and like Q at any other number.
I wish I could explain it that well. That was beautiful. How do we calculate Q for something not at standard conditions? The same way we have throughout the class. It's just concentration of products raised their molar coefficients divided by concentration of reactants raised their molar coefficients. That's it. Of course, yeah, you would need to know like what the concentrations are to be able to calculate it.
Do we have other questions? We can definitely wait a little bit if you guys like want to kind of like take it in and think about it and have questions, you can always ask. Also, if you need to go back to any of the slides, let me know.
Wait, sorry, someone just asked if delta G naught is negative, you're going to have more products or reactants at equilibrium. If delta G naught is negative, then it's like over here, while equilibrium's over here on the right. So you're going to have more products and reactants at equilibrium, which you can see in.
So here the val is going to be delta G is equal to 0, right? So you can see where it falls.
Yeah, but wait, sorry, can you move one more forward? Like where I had the, yeah, okay. So if delta G naught is negative, then you see we're at like this curve on the left. So there's more products and reactants at equilibrium. And if delta G is positive, then we're looking at the curve on the right. So there's more reactants than products at equilibrium. We're at the same X value on both of them. How do you calculate delta G from pressure of only products? Question 10 on homework 8. I haven't looked at the homework, but I'd assume that maybe the reactants are in the liquid or solid phase. So maybe you could calculate Q using only the pressure of the products, and then you could use the equation delta G equals delta G naught plus RT on Q to solve. But I shouldn't like give you an explanation without having seen the question. So I'll look at that after. And then, sorry, there's another question. Is change in moles for the Kc and Kp relationship, including moles of solids and liquids, or just gases and aqueous? Concentrations for liquid and solids don't change. So they don't show up in the Kc and Kp equations, even though they will show up in your Rice tables, because you can change the number of moles without changing the concentrations. And the Rice tables uses change in number of moles. How does rate of condensation increase when we decrease the volume in the piston? Okay, if we decrease the volume, then we have like N over V, right? Is like the density of the gas molecules. So if we decrease the volume, we decrease V, and we haven't changed N. So density is going to go up. And when we increase density, we increase rate of condensation. So that's why that would go up. And you can also think about it as like, if we decrease the volume, there's going to be like more molecules near the surface of the liquid at any given time. So higher frequency of collisions and higher rate of condensation. Sorry, I'll let you guys ask some questions now. I'm sorry, I keep talking too much.
Yeah, there's a pretty similar question to that if you want to also look at that one. Why is that the volume does not affect the rate of condensation and the rate of evaporation in closed system? Is it because it affects both equivalently, or are the phase changes completely independent of volume?
Can you repeat that one more time? Is it in the chat?
It is in the chat, I think.
I can't find it.
Okay, you should be able to see.
Did you send it to me? Thank you. Why is it that the volume does not affect the rate of condensation and the rate of evaporation in a closed